The first electrophilic addition we'll talk about is addition of hydrogen halides onto alkenes. As we've already seen, the mechanism is pretty straightforward. The first step is protonation of the double bond, which can occur by the nucleophilic attack of the double bond onto the hydrogen, which gives us the intermediate cation, which is then attacked by X-. This can be chloride, bromide, or iodide, to give us the final product. So the mechanism is pretty straightforward, but in cases when we have unsymmetrical alkenes, there is some chance of getting a mixture of products, and this indeed does happen. So if we have this methyl cyclohexene and react with hydrogen iodide, what we'll get is the more substituted, the less substituted iodide and the more substituted iodide as well. Question is, which of these two products forms predominantly, and the answer is the more substituted iodide forms as almost exclusive product in this reaction. This turns out to be a general rule, and this rule is called Markovnikov's rule. And it basically states that addition of species which can be written as HA in general form to a CC bond place hydrogen atoms onto the carbon that already has more hydrogen atoms. Now, what does this mean practically? Well, if we have a system like this, where our double bond has one carbon atom which has no hydrogens, and the other one has CH2 group, then addition of HBr here, according to Markovnikov's rule, will proceed to place hydrogen bromine onto the more substituted carbon and hydrogen onto the less substituted carbon to make it even more hydrogen. Now, what is the actual explanation behind this? The explanation again is provided by the mechanism, because if we look at the possible routes of protonation of this alkene, then we can protonate it according to Markovnikov's rule on the less substituted carbon, which will then leave the cationic center on the more substituted carbon. And so this will give us a tertiary cation. Alternatively, if we protonate the carbon which is more substituted, then we'll get the less substituted cation, and this will be a primary cation, which is of course less stable, so this is the species that we get. And then proceeding from here, we'll end up with the attachment of bromine onto the more substituted carbon to give us this intermediate. Okay? This reaction is an example of a regioselective reaction. When we have two possible orientations of addition, one of them is being preferred, and this is an example of regioselectivity. And this is one of the issues that synthetic chemists try to attain. Reactions that are regioselective and stereoselective. We can also see that in this case, Markovnikov's rule is basically guided by the formation of the most stable intermediate, which is the tertiary cation, in this case, from where things proceed in a pretty straightforward fashion after that most stable intermediate is formed. This works for any hydrogen halide, so it works for HBr, as shown here, HCl, or HI equally well. Now, to make things a little more complicated, in 1933, Karash observed that in the presence of light or peroxide species, and peroxide species are known to form radicals very quickly because the OO bond is weak, HBr can add in a different way. And this will be so-called anti-Markovnikov addition. In other words, if we had this example, and we created this with HBr under the influence of radicals, what we'll get is the attachment of bromine onto the less substituted carbon. So as anti-Markovnikov addition. How does this work? Clearly the explanation for this should again be looked for in the mechanism, and we might assume that the mechanism is not going to be different from the one that we've seen already when we got Markovnikov problem. The real clue comes from the use of light or peroxides, and that they are really something that should strongly suggest to you a radical mechanism. And so the first step in this reaction is the decomposition of this peroxide into two alkoxy radicals, which then react with HBr quickly to form the most stable bond possible, and this will be OH bond rather than OBr bond. This now leaves Br dot as a free flowing radical, and Br dot is going to add onto the double bond. This is standard radical mechanism. But in this case, Br dot will now react to with another molecule of HBr to abstract the hydride and to get us to the final product. However, in this case, as you can see, the roles of partners have been switched. Although both the Markovnikov and this anti-Markovnikov addition of HBr adds HBr over the double bond. In the case of Markovnikov cationic addition, the first step was the addition of hydrogen. And so hydrogen was the addition of hydrogen was the one that needed to happen so to give the most stable cation. Here, addition of bromine is first, but still the requirement is the same. We need to get the most stable radical. So if we look at our original example, and focus just on the bromine addition in this step, we could add bromine onto the more substituted carbon, which would leave us with a secondary radical here. Or we could add this bromine onto the less substituted carbon, which would leave us with a tertiary radical here. And not surprisingly, this one is going to form predominantly and will ultimately then lead to the product that we did observe, and this addition of bromine onto the less substituted carbon. And so this is an anti-Markovnikov addition. And an important point, and the one that we've seen already, is that radical reactions differ quite a bit in their energetics. And if they're unfavorable, they're just simply not going to happen. And the anti-Markovnikov addition is favorable only for HBr. So that means that it does not work for HCl or HI. Okay? So to sum this up, we can add HCl, HBr, or HI over the double bond to ionic addition, and that will place hydrogen onto the less substituted carbon and bromine, iodine, or chlorine onto the more substituted. Alternatively, and the clue for this will be presence of peroxides or light, we can add hydrogen bromide, and hydrogen bromide only in the antimechanical fashion. This proceeds through a radical mechanism and places bromine onto the less substituted carbon, while hydrogen goes to the more substituted. Now, in the next subtopic, we will see a relatively related reaction. We'll see how water can add over the alkene double bond as well.